So I shall speak about the efficient computations. That is very much similar to what we have heard already, but it is applied to advanced engineering design. And maybe if there are to structure of the machines, but I'm convinced that in the near future we shall see even the design of structure of materials on the micro or nano level. So I shall start with the problem of innovation management. So certainly the goal of product development and manufacture is to sell it with profit. The key for successful sale is innovative product, but how to manage the innovation process. Certainly the key property is minimize time to market, but how to solve the conflict between innovation quality and reduce time to market. Certainly, there is always a danger of coming too early or too late to the market. So if you have a current product, you can come with your innovative product very soon or very late. In between is coming your competitor. And if you come in reasonable soon time, so you have potential benefits, but always you have some potential market losses. And if you come late, it will be almost only losses. So critical issue is to decide whether to do large or several smaller innovation cycles, and how to increase innovation in content and not increase time to market. So my answers to these questions are to apply advanced design methodology and efficient scientific computing, about which I shall speak. So possible improved design process, traditionally it is described that over the time of the product development, there is a percentage of the design freedom you have and about the design knowledge. Traditionally, the design freedom is being decreased up to almost zero, and at that time you have complete knowledge how to do the product. So it's not from this point nice, and the question is on the right hand side how to do it in an advanced manner, and I shall show you that we have succeeded to do it in this way. That means to enable during the development to again increase the design freedom, to gain new knowledge during the development process and apply this new knowledge into the design freedom. So how to improve design process? The key issue to get there, what I have shown, is to have a higher design efficiency, and we can achieve that by four approaches: structuring the design process, faster calculation tools, mighty criteria optimization, and knowledge mining. And this can lead to shorter time to market on one hand side, or vice versa. You can keep the same time to market, but increase the number of variants that you would investigate, and by that way increase the quality of your innovation based on gain knowledge and reuse them. So advanced design methodology is coming from analysis of standard configuration design for complexity reduction. So configuration design is a standard procedure in each design approach. It's a fact that from some parameters you compute from dependencies and other parameters, and these computed parameters must fulfill some constraints, and you maybe, if constraints are not fulfilled, you have some fixes, and over all of this computation you have some global cost function for optimization. Here is an example of a benchmark of a relatively simple design network for elevator into a building. And we develop such networks for preliminary design of vehicles or for machine tools, and the number of parameters are ranging from hundreds to 3,000, for example, for the vehicle. So computational complexity of configuration design is in fact in principle exponentially growing. For example, if you have just 10 variables and 3 potential values for each variable, so and non-monotonic constraints, you have easily design space with exponential size. So how to reduce this computational complexity? One way is parallel computation. I shall show something about that, some sensitivity analysis, but key approaches we have found is decomposition of the design space into hierarchy of design problems, sub-problems, global evaluation, and then finally global computation and evolutionary algorithm. Here is a demonstration what I mean by the decomposition of the problems. So in this axis are key parameters of the design. Here are the constraints they must fulfill, and it's difficult to start to solve for something because everything is dependent on everything. If you reorder that, you can find that there are some islands that are only loosely connected, and inside the islands are happening the main iteration. And because islands are smaller, the exponential growth is limited, and you can tackle the computation. Everything is done in the based on the investigation of parallel kinematic machine. Here are some illustrative figures. Design network for such parallel kinematic machine is consisting on some parameters in kinematics, in structural design, material selection, control parameters, and here is a lot of different constraints from workspace collisions to control dynamics and control accuracy. And you see that it is interdependent, and if you apply traditional approach, you find that everything is depending on everything, and it's becoming quite complex to moving forward in the design and to fulfill all the constraints with reasonable parameters. So we investigated this conflict levels, or we have found the conflict levels inside this design space, and we decompose this design network into islands and realize the iteration inside each island, and then only several iterations between islands. So in principle, we have found that we can distinguish geometry, connected as well with kinematics, and structural design connected maybe mainly with the stiffness and eigenfrequencies, and then actuation connected mainly with the dynamics, control accuracy, and so on. And we can then, we shall see later, compute that on each level in the islands and reduce the computational complexity. So the other fundamental approach is usage of global computational tools. That means I'm not interested in computing for some selected parameters of the machine for one position inside the workspace, the properties. It's too little for a design process. We need to compute for maybe for selected parameters and one moment the properties on all workspace, and moreover not the values. We are interested in the, for example, minimum or maximum values. So and at one procedure to immediately compute the minimum stiffness inside the whole workspace, or minimum accessible acceleration inside workspace, and these values are the decisive values for design process. So in fact, we must have, I'm speaking about global computation and global map of solution. We have succeeded for very demanding properties like dynamic capabilities or stiffness to have such procedures for global computation. So such maps inside the whole workspace can be computed much more efficiently than by traditional ways, step by step, for solving finite element models or step by step solving the differential equation for motion and so on and so on. It's one approach. The other approach, we have succeeded to improve the multi-body dynamics, the computation on parallel computers. So here, the problem of parallelization of the solving dynamics, solving in differential equation, is that there is some improvement, but very soon, after only several number of increased processor, is saturation of the speed up of the computation. But we have succeeded to show that, for example, multi-body dynamics for reasonable size of a vehicle can be on 10 processors, so 10 times quicker, so 10% of the time is necessary, or on 20 processors only about 5%. Really, the saturation, as you can see, is very small in a fraction of percent, and this is very much convincing us and encouraging that this approach is efficient. Then certainly evolutionary optimization, we have heard about that a lot. So Pareto set and finding that Pareto set and compute that by evolutionary optimization. But I should like to stress maybe another issue, that we have found that we are evaluating the Pareto sets for some expected properties, and but at the end we are analyzing the overall computed cases. So we are not throwing away the results of optimization because they have deep knowledge inside. In fact, we are trying to get some analysis of the knowledge included in that, and by that way to gain the new knowledge. Certainly, whenever you have a Pareto set, you must somehow decide where to place your design. So some approach how to find an optimized position on the Pareto set in this way, or find maybe a change of the slope and the Pareto set. Here is some example showing that we are computing Pareto set between acceleration and stiffness. Here is about 30,000 variants of the parameters of machines evaluated, and based on that, however, we have investigated also other properties or other parameters. And for example, we shall see that we have found that the angle surprisingly is a new knowledge and is changing the stiffness significantly, and we have used that as a gain knowledge from the design process. So from the middle of the design, we are returning to the freedom of designing. Design methodology for parallel parallel kinematic machines is based. Now we are speaking about geometry conflict, structure conflict, and actuation conflict in hierarchy. What I have shown before, that we can see how it is really done. That previous step is fixed, then on top of that is optimized or solved the next step, and so on. And only in fewer cases you must return back. Computational tools. All these properties must be computed efficiently, globally, in order to get it into the evolutionary optimization. So here are examples of results of global computational tools. And how it was applied in order to get the Pareto set or the new knowledge. The new knowledge was that the angle of the slides, if it is not parallel, if it is skewed, then it is contributing to increase of the stiffness. Here are another tools that we were using. That means visualization in case of multiple design criteria, or how to tackle the Pareto set with multiple design criteria with multiple performance indexes. So now a case study of our machine. So it was required to design a new horizontal machine center, and it was some starting properties that was a dream or goal, and some dream parameters I have shown at the end that really we can achieve even this dream parameters. The question was whether new concept could simultaneously improve all mechanical properties and become the concept of future machine tools. In fact, we started with some inspiration. We started with some initial concepts. They were elaborated from equal actuated machines, the same number of actuators, then the number of degrees of freedom, up to over-actuated machines, redundantly actuated, that is significantly improving the properties of a parallel kinematic machine, but certainly the cost is more actuators and the difficult control approach. Here was some variants, conceptual variants, and each conceptual variants were investigated by this Pareto sets and 10,000s of parameter variants, and only after such optimizations, results of these concepts were compared. Finally, we decided for this fourth variant because surprisingly the previous variant were improving dynamics but not too much stiffness, and it's a wrong way not to improve stiffness if you have more rapid dynamics. So we came to this variant 4 that was offering potential for improvement both. And we apply our design procedure. I would stress here only that above 50 structural concepts or sub-concepts of the previous main conceptual variants were investigated, and more than 100,000 parametric variants. In order to compute in order to compute, for example, this Pareto set for some variant, it was only maybe 30,000 variants, and we were capable to compute that in about 3-4 hours. So it was very rapid computation and capability really to the designer, provide designer with almost real time of design with some optimized results. Now return back to this innovation potential, development capacity. I have compared the traditional approach, how many variants are investigated during the design process, and how many variants were investigated for our new approach. And if I compute the integral over the space of variants, we can see that it is from 100 to 60,600 times increase the potential. Here is even with some data, this change of traditional dependence between the freedom and knowledge into a new way, and it was really achieved, and we were capable to this correspond to these particular variants, major conceptual variants being investigated, and at the end it enables us to reach the final variant with wonderful properties. Before that was one decision. One decision was that we have redundant actuation with 3 actuators for 2 degrees of freedom, or just 2 actuators for 2 degrees of freedom. it was decided that the improvement is only about 10–20%, and it's risky for new technology. On the other side, we have realized that if I'm going from the parallel sliders into skew sliders, we can gain again 20% more. So we finally decided to use this skew variant with the non-redundant actuation, and we achieved this even from the increase potential 20% more. So it is again skew variant and this parallel sliders variant. You can see how we are selected. Then final selection was in this angle of the slope, change of the slope, but it was not exactly on the boundary. It was a little inside the space, because there was advantageous property of symmetric workspace and machine space for simpler design of components and control. So here is the overall how it is, how large is overall machine, and it was a presentation on the European manufacturing that we did in intensive verification between computation and measurement, and really we are very happy that our prediction was fulfilled. So we have achieved lowest stiffness, doubled the traditional stiffness, 120 newtons per micron, and the lowest eigenfrequency was also doubled, was 100 hertz, and you see here 5 first eigenfrequencies, how they are uniform across the workspace. So it is very promising. Here we can say that we see Pareto set of real design machines on the market. So these are traditional machines, this new machine trijoint, and maybe some future machine with a redundant actuation. So here you see that from traditional machine to this new machine was really doubled all the mechanical properties. And this sliding star, this new one can bring even 50% more. So here are some consideration how nicely were improved the properties. Everything was doubled, and for the first time it was capable to do it simultaneously. So in fact, overnight, all mechanical properties of a traditional machine was doubled. It's from my point of view almost incredible. But important is that new design methodology was verified, and it was using this increased potential of efficient scientific computing using this genetic algorithms and Pareto multi-criteria optimization, global computation, and based on that, it's much more improved. In future, we can even double that and go into incredible values. Question is whether the manufacturers of machine tools and users of machine tools are capable to use it at all, because we are maybe capable to design more than they are capable to use. Going to the conclusions, lesson learned is that always it's, from my point of view, worth to realize a complete cycle. So start from the reality, generalize the problems into theory, find the innovative applications, both in the fundamental research approach as well in the application research, and come with these results back to reality. And the key bone of that was efficient scientific computing that enables to increase innovation potential in advanced engineering design. And it's my conclusion from that experience that really any increase in computational capacity, capability, efficiency is capable immediately to contribute to improve innovation and design process. Thank you very much for your kind attention.
Yeah, thank you, Professor Valášek, for such a nice presentation. I invite questions from participants.
Shanko, can I ask a question?
Yeah, sure. Go ahead.
Professor Valášek, thanks for this excellent presentation. Maybe later on, I will get some more chance to discuss this with you. You are doing some very involved multi-objective optimization. What kind of algorithm you are using for it?
Very, very simple genetic algorithms. So
I see. I see. You mean something?
There might be a space for progress.
Yes, looks like that. These problems are very complicated, interesting, of course, more inclined towards mechanical engineering than materials. But even then, since I deal with multi-objective optimization, I can see how complex and how useful they are. Probably some meta modeling can be done for the objectives, and then, a lot of things can be done. Anyway, thanks for talking about it. It was very nice, and I appreciate for educating us on this special domain of application. Yes, thank you so much.
Yes, true. Certainly, I see that there is a bridge to materials, because now with the 3D printing, printed materials, you can think about including actuators inside materials. So to array of actuators, and how to design it, how to control that. Or we did investigation of cable trusses. That means you have a truss, and you place some beams with cables, and this could contribute immediately to design on the micro level of the 3D printing. So to print something that is not capable to withstand buckling, but is reducing the weight. And immediately you have somewhere on the bridge from machines to
materials. Exactly. That is what design is all about. Using this conflicting objectives so that you can come up with an excellent Pareto front and provide good solution. Anyway, I'll personally discuss those things a lot more, I hope. But again, thank you for this beautiful presentation.